Our second speaker is Kunal Chawla, and he will talk about detecting stationary measure classes.
So thanks everyone for coming, and I'm grateful to be invited. I just want to spend some time today talking about some thoughts I have related to some ongoing work on singularity of measure, of harmonic measure. So first I'll describe a bit of the background and the problem, and then I'll mention stuff I'm working on. So first, this is fundamentally a problem about random walks on groups. So first I'll just recall some of the basics. So let's say that G is a finally generated group. G is a finally generated group. And we have mu is a probability measure supported on G. Let's say it's generating. Then you can find the following stochastic process. Wn is just a sequence of products of IID random variables, all drawn according to this measure. Okay. So we're interested in the case where G has some interesting action. So let's say that G acts on some space X, which we'll say is hyperbolic. And for now, today we can just think about the case where the space X is, say, locally compact and geodesic. Now, it's a classical result due to Furstenberg. Furstenberg in the 60s, that if you take the following process, if you take the sequence, if say O is some base point, and say you take W in here, the sequence will converge to some point, random point on the boundary of X, almost surely. And so this is proven really in the Lie group setting due to Furstenberg. The proof works in the case where X is proper and hyperbolic. When X is not proper, this was a result of Mar and Tiozzo in 2017, and then again in the Gazelle in 2021. So first,
convergence lemma in general hyperbolic settings, isn't it due to Vadim?
Oh, sorry. Yes. That's a very important. I should do Kamanovich. Yes. Thank you. So this defines a natural measure on the boundary. So you get a measure given by mu A is the probability that this random limit is in the set A. So you have some natural measure defined on the boundary, and this measure will be stationary. So this measure mu satisfies the following equation. If you take a look at the action of mu on here, this will be equal to so it's natural to ask, given this measure defined by this dynamical system, what can we say, how do the properties of this reflect the group? And so, or for instance, given some other natural reference measure on the boundary of X, how does this relate to other reference measures? So when G is, say, the fundamental group of a hyperbolic surface, the boundary of X is a circle, you might ask how it relates to like the Lebesgue measure, for instance. And so it's a theorem due to Furstenberg, that when you have a semi-simple Lie group, and you have, say, gamma is a cocompact lattice, then there exists a measure mu, finite first moment, such that this corresponding hitting measure, harmonic measure, is in the Lebesgue measure class. And so this was fundamental in proving sort of basic rigidity results of Furstenberg, and then it was used in Margolis's first proof of superrigidity. So then, and the question of singularity of this harmonic measure is related to various other natural questions in dynamics. for instance, they're studying measures of maximal entropy on Julia sets, or continued fraction expansions, or say studying harmonic measure for Brownian motion on negatively curved manifolds, for instance. And so you might ask, and so there are various other results in this direction, which I want to mention. But first, I want to mention the following question. And the history behind this question is sort of unclear to me, but it was first stated in a paper of Kamanovich and the Prince back in 2008, given, well, more of a conjecture than a question. Following conjecture, given any finitely supported mu on SLDR for d greater than equal to 2, they conjectured that the corresponding hitting measure, mu, is singular at infinity. At infinity. And variants of this question for, say, different groups or groups acting on certain spaces, say the mapping class group or various lattices, have been sort of intensely studied over the past couple of decades. And I want to just mention a few of the important references. Now, there are many sort of papers studying similar questions, and unfortunately, due to time constraints, we won't be able to mention them all. But I will try to mention some important ones. So, first of all, a very important paper of Chatterjee back in 66 showed singularity for random continued fraction expansions. So we take a continued fraction expansion with a simple number, or if you generate a continued fraction expansion given IID coefficients, these two measures will give you sort of singular measures on R. Then it was a result of Guvarch and Lejean. That if you have a subgroup of PSL2R, or the symmetries of the hyperbolic plane, which is cofinite but not cocompact, so it has a cusp. So this quotient has a cusp. Then for any measure mu of finite first moment, corresponding hitting measure is singular with respect to the bed. Okay. Now, this has also been studied, so you can sort of view continued fraction expansions as a random walk on SL2Z, which we view as a lattice in SL2R. And so this is really sort of very similar results. Now, in other cases where you have cusps and sort of singular measures at infinity, one can show that, let's say, if you examine the action on the mapping class group on technical space, you might ask about regularity of the measure on PMF. So it's a result of Bob Gardner, Joseph Mayer, and Giulio Tiozzo. Showed singularity for finite first moment measures, or finite first moment measures on the mapping class group with respect to like the Lebesgue measure class. Now,
What's the physics text?
sorry, the full statement. So if you have a measure mu of finite first moment, and if you look at the action of the mapping class group on technical space, well, this converges almost surely to infinity, so you get this measure on the boundary, and so you can define the Lebesgue measure class. So you can define something locally And so you can ask
I'm
about,
still assuming, this finite support is only in that question or it's everywhere?
I'm sorry.
The finite support,
So this statement is for finite first moment, but you can ask this question.
Better result was not for finite support, right?
Yeah, this is not for finite support.
Okay,
It's
that's-
finite first moment. So yeah, finite first moment. Now, on the other side, now one can observe that this conjecture was stated purely for finitely supported measures on the group, but really you need to restrict to lattices in the group to ask this question. Because there is a result of Bourgain, a construction due to Bourgain in 2012, who constructed some mu supported on SL2R, SL2R, which is finite support. But generates a dense subgroup such that mu is absolutely continuous at infinity.
did Tom Wolfe do something on this? Are you familiar?
Um,
One of his last papers was,
Oh.
yes, I
okay,
have it somewhere.
okay, I'd be happy to.
It might have motivated.
Oh, okay, I didn't know the story behind the paper actually, but I'm be curious to hear more.
Yeah,
Yeah. So you need to adjust this question slightly. So now I'll ask the following question. So I'll get some. So now, today I'll be discussing the following question. Given any finally supported mu on not SLDR, but on a lattice in SL2R. So I'll just be discussing the rank 1 case. What can you say about the regularity of the measure? So can you get something absolutely continuous? And so in this direction, there are sort of very few results. It just, the point is that all of these sort of singularity results, many of them use really the same sort of idea.
all right, you were emphasizing the cusp. Are you assuming compact support, compact quotient or finite volume? You need the cusp.
Yeah. So if you have a cusp, it's known that it's singular.
Okay, so you're gonna.
I'm focusing on.
Compact quotient.
Yeah, thank you. Cocompact.
So it's the cusp that's the source of the singularity.
Yeah, exactly. And I want to highlight the ideas, which you can.
This is related to the relation between the word metrics and the
Yeah, exactly.
geometric metrics.
Yeah, the idea is you look at the. Yeah, so you take a look at the geodesics in your space, which according to the Lebesgue measure. And so what you do is you take a look at the geodesic and you ask, how long does it spend inside a small neighborhood of the cusp? And so you can define two metrics on the group. One is the metric coming from the action, and one is the metric coming from taking this cusp and just collapsing it. And so what Gardner, Mayer, and Fiozzo showed is that if you look at the if you look at the distance in the group over this distance where you quoted out these cusps traveled by the random walk, then this will go to infinity. And so this gives you your source of singularity.
Is this related to the work of Lebesgue and Prasad maybe, and about word metrics with when you put the cusp, it's very different when you compare quotient and the comparison. Is it related?
Yes, yeah, it is.
So their theorem, how different is that theorem from the other works?
Well, I mean, you need to show that the random walk sort of witnesses this in order to construct the singular set. So, I mean, you know that these metrics are different, like.
They show that.
Yeah, exactly.
Okay.
So the idea is most of these works are sort of similar in this sense. And so definitely in the cocompact case, you don't have this cusp to use anymore. Right. And so you need to find other techniques in order to actually produce singular sets. So most sort of techniques have relied on some form of thermodynamic formalism or some way to get bounds on the Hausdorff dimension. of the harmonic measure. And so one of the main tools is this theorem due to Lancher, Sinsky, Matthew, relating the question of singularity of measure to estimates on the green distance. So given a measure, you can find the green distance on the group as the following. The distance here is equal to the expected number of, well, negative log of the expected number of hits to G. So the expected occupation time of G divided by the expected number of returns to the origin. So this will define a metric. And so now this metric reflects properties of the random walk.
You allow non-symmetric measures.
You can ask for non-symmetric measures, but let's restrict to the case of non-symmetric measures so that this is actually a metric.
Sometimes one call it as green metric,
Yes.
but it's not it's symmetric.
Yeah, very often people call things metrics, which are not symmetric. Yeah. So I'll paraphrase part of their theorem. They show some long sequence of equivalences, but part of what they show is that if you have, say, the Patterson-Sullivan measure on the boundary, Patterson-Sullivan measure.
I'm very confused.
Oh.
To me, the Patterson-Sullivan measure, if you're a lattice in SL2R, it's everything. So I guess there's some subtlety, like Patterson-Sullivan don't discuss. In their situation, gamma is always not a lattice.
Mhm.
It's a discrete group, and then there's the limit set. The limit set's everything here.
Mhm.
So what are we talking about when you say Patterson-Sullivan?
Oh, the particular measure you get, like the measure class.
But can you show me how you construct it?
Sure.
Take an orbit, but obviously weighting it in some way.
So you take an orbit and weight in some way, so you take the sequence of measures. Again, you think this sum weighted in the appropriate way, G of sub n, and appropriately weighted. You take some weak energies. Oh, sorry.
Yeah, so in the lattice case, this has got an asymptotic. I'm just surprised that we're talking about lattices. I mean, Patterson-Sullivan is all about not lattices.
Right. I think
And that's what's confusing.
I think the point here is that their setting here is you have some hyperbolic group and you're looking at some measure, you want to construct some natural.
In a more general hyperbolic group setting, I agree with you, but in the case of, I'm thinking of it in SL2R, the case you're going to be talking about.
Right. Okay, so in the SL2R case, you can just take the Lebesgue measure. Okay. So I'll just say the SL2R version. So the following are equivalent. One is that
I don't want you to change it. I just want to get rid of my confusion.
oh, sorry. Okay.
This theorem, in which context are you giving it? We're still talking about SL2R and
A lattice in SL2R. The compact quotient of SL2R. I actually know what that is.
Yeah, okay. Sure.
So I'm happy.
I was going to give it in the hyperbolic group case, but I can say the SL2R.
And I do it in what you want. It's just.
do what you want. Just.
The point is that you raised that question in SL and R, and then you said a lattice, so then I'm thinking of the linear case. And now, so in that case, in the linear case, if I have a lattice in SL2R cocompact, the only Patterson-Sullivan measure I know is the Lebesgue measure.
Right. Okay. So I'll say the hyperbolic case. So say we have the Cayley graph for a hyperbolic group. And let's say that rho is a Patterson-Sullivan measure on the boundary of the hyperbolic here. Okay. So the following are equivalent. One is that the harmonic measure. So sorry, let's say that mu has finite first moment. For mu of finite first moment. One, that nu and rho are mutually absolutely continuous. And two is that the green distance and the word metric, so let's say this is also symmetric. Is that these two are almost similar in the following sense, that there exists some C greater than 0, such that this word metric times green metric okay, is bounded by some set. So the point is, we have, and this is only part of their theorem, it's really paraphrasing part of it. But this is really the statement you want to use. One is that they relate the sort of coarse geometric property of being mutually absolutely continuous at infinity with this sort of fine scale property of the green metric and the word metric being almost similar up to a v-scaling. Okay. And this is really one of the main tools we have. So, and this tool was exploited in some recent work of Senko and Tiozzo, which are some of the only results we know in the cocompact case. So the theorem, Senko and Tiozzo, for some class of measures, for some finitely supported measures, on some cocompact lattices. So in particular, the things they construct are of the form, you take some polygon, symmetric polygon, you look at these particular side plane transformations, and you look at measures supported on here, and for some and you show that any measure supported on here, which is symmetric, is singular at infinity. And so they found some very clever way to use the color lemma, and together with this theorem of Plancher-Hessian Matthew, in order to just find some particular elements which witness failure of this, and then deduce that these two measure classes are singular.
It's that if you just want some finitely supported measures, that's sort of trivial to do. Right?
Sorry, I mean,
there's no something.
Oh, sorry. I should clarify. It means that you pick the support, and it's like all measures are supported on this particular finite set are singular. Some supports. On fixed support, on some with this fixed support.
I'm confused about the role of the group. That's a fundamental domain for
Yes.
the octagon or something. Genus 2. What are you saying that?
He picks a particular set of generators of the group that he likes, and then he only allows random walk that use these generators.
Okay, and then you.
So that's not.
And then that does. Okay, and it's an example. Okay.
Yeah, and so they have some sort of crude estimates on the green distance coming from just a comparison with the free group.
Yeah, so you're comparing the two, the sort of geometric and word distance, on this compact at this fine measure.
Today, I want to discuss some other tools for singularity. Okay. But the point is that there are very few tools which we have in the cocompact case, or general tools which apply in the cocompact case. And so most of the results are sort of very ad hoc. You come up with some particular sequence of things. And so today I want to discuss maybe an approach to try and show singularity. So this approach is inspired by the study of quasimorphisms, which is really sort of, I mean, a lot of it was pioneered by Basvino and Fujiwara, but now I just want to define some particular maps and use these maps to try and witness singularity. Let's say we have some, so now we're back to the case of some G, which acts on some X, which is, we'll say, and this action is proper, and X is hyperbolic. Now we're dealing in this setting. What we do is for any group element, G, and for some D, which is 0, which is some positive number, we can find the following. We can find this function which takes in 2 points as input, and outputs some number which essentially counts how many copies of a translate of the path O, so some translate, path O, gamma O, you see on here, gamma 1, 2, O, gamma 2, GO. See on here. So more specifically, this is defined in the following way. So given a path alpha, we can define some norm, which is defined as the number of disjoint. So say this is parameterized by some interval. You find the number of disjoint subintervals, such that if you restrict the path to those subintervals, you get exactly a copy of this particular chosen path. So it's the number of disjoint copies of this path O, G, O along alpha. So now my function CGD is defined as the distance between x and y minus the infimum over all paths alpha with n points x and y of the length of alpha minus d times this one. OGO. Okay. So this is we use to define quasimorphism. So for instance, the map CGD minus CG inverse D will define a quasimorphism. But now I just want to use sort of one part of this path here. And so now the key observation is that this function is subadditive. It's called subadditive. So if I take my random walk, so if I take a random walk with finite first moment, what I can do is I can examine this limit of 1 over n times CGD of Wn. This limit is almost surely equal to some constant. And now I want to use this to try and probe at my harmonic measure. Now, I can do many transformations to this which preserve the harmonic measure, so I should take this and divide out by the drift of this. And so this will almost surely converge to some constant, C, let's call this C tilde, GD. And this function, it's not immediate, but this depends only on the measure class at infinity. So this is really a function of nu more than anything else. And so because of this almost sure convergence, if you have, so if for any 2 mu1, mu2 of finite first moment, if there exists some G in the group and some D greater than 0, such that these two numbers are different, according to the single harmonic measures of these two random walks, then this implies that these two measures, nu1 and nu2, are singular, are mutually singular. Okay. And so, for instance, because it's now relating to the you get measures on cocompact lattices of finite first moment, which give you Lebesgue measure infinity. So for instance, if you were to find some group element G and some number D, such that if you were to take some finally supported random walk and witness that this is different than the corresponding measure for like the geodesic flow, then that would give you an approach to cocompact singularity. And so my theorem today is to argue that this method is sharp in the following sense. That if I have two harmonic measures which are singular at infinity, then I am able to detect it using one of these statistics. So this is my main theorem. So instead of G acts on space X, which is, so the action is proper, and the space is hyperbolic.
Wait, sorry, what were the statistics that you could use to detect that they're usually singular?
So for every G and for every D, I can construct this map,
Okay,
and this I get just some number here.
okay.
So I guess for any G, I can take D sufficiently large, maybe eventually integers, and I get some countable family of numbers.
Can you remind me again, can you just repeat what the definition of this function CGT?
Oh, yeah, sure. I take the distance between X and Y and I subtract the infimum over all paths with endpoints X and Y. The length of alpha minus D times this norm, which essentially counts the number of disjoint copies of GO along here. So this function is overall.
I can't read what's written there.
Oh, sorry.
What is the subscript of the norm?
Oh, sorry. This is I'll write it more clearly. I take some path from the base point times G to G times the base point. So basically just a translate of G.
And can you, and I didn't quite get the definition of this norm. What is this?
Oh, I take some parameterization of alpha. I ask the number of disjoint subintervals of my parameterization, such that if I restrict to that subinterval, then I get exactly a parameterization of this geodesic from O to GO. Now, because I'm taking an infimum over all paths, I have flexibility to rearrange alpha. The point is, essentially what you would like to do is say something like, I take the number of copies of this blue segment within some bounded neighborhood of this, but this is the way that you make such a thing work. Like in a way that's like subadditive and really define something.
So it's the number of times that the G translates come within that bound?
Yes, essentially. Yeah, but you have to be sort of careful the way you define it like this. But so this is why you need to take this like this slightly different thing. Yeah, it's essentially counting this. Is that clear or no?
So D is fixed and G is fixed.
Mhm.
Do we also fix a geodesic from?
Yes, we also fixed the geodesic from O to GO. Yeah, so this is fixed. It's geodesic we take.
That's the blue path that you do.
Yeah, this is the blue path. Yeah. So I count the number of translates of this blue path within some bounded neighborhood of my geodesic, essentially. Right. So the main theorem is the following, saying that if I have two measures, mu1, mu2, finite first moment, and look at the corresponding harmonic measures. So let's say that mu1 is mu1 stationary, and mu2 is mu2 stationary. Then v1 is absolutely continuous with respect to v2, if and only if for every group element G, and for every D greater than 0, let's say D, greater than 0, this limiting statistic, these two limiting statistics are equal. And so one direction of this is easy. If for one of these statistics, these two things differ, then I just get a singular set right away. And so the content of this theorem is saying that I can always, if these two things are singular, then I can always find such a G and such a number D. Okay. And moreover, you can say sort of more refined things. You can also show that two less than is usually continuous with respect to mu2, if and only if for all G in the group, for all G greater than 0, its limiting variance of this map are also the same. So this is like an expectation statement, and now I look at the variance. The variance of C D. If I take the random walk, this is random walk distributed to the first measure over n times the journey. Given by this variance with respect to the second measure of CGD. Divided by n times the drift. And so there are some interesting consequences of such a thing. Is the statement at least clear? And so here are some corollaries of here's some consequences. Because some of these don't directly follow from the theorem, but some of these will follow from the method. So using the same proof here, we can also recover a version of this result of Blanchard, Hersinski, and Mathieu. So we show that the following are equivalent. 1. And so we're in the same setting. We have two measures defined at first moment, and I have two harmonic measures. If I have two harmonic measures, which one is absolutely continuous with respect to the other, one is that this is absolutely continuous with respect to here with a bounded density. And 2 and 3 is that maybe after rescaling, if I take the corresponding green distances, so this is the green distance with respect to the first measure, ID G minus maybe rescaled version of the green distance with respect to the second measure, that these things are most some bounded in multiple ways from each other. So there exists C greater than 0, such that for all G in the group. So things are roughly similar. And moreover, the proof here is very like elementary, simple. It's essentially a probabilistic construction of such a measure mu. But before I get into the proof, I'll mention one more relation to some other work. So this is also related to some recent work of Timothy Bernard, who examined winding statistics of the geodesics on the surface. So what he showed is that the measure class, so for any mu finite first moment, this is also on a hyperbolic, say, given any, what I do is I project G to its abelianization, and then I tensor this with R. So then I can ask about the expectation of I mu, because this just makes sense on this finite-dimensional vector space. And so this thing divided by the drift, one is when you take this and divide by n times the drift, is determined by the measure class. By the measure class. The class of mu. And moreover, you can say the same thing about the limiting about the variance here. But the difference here is that one point is that the reason, one thing sort of remark here is that we get an if and only if. But for instance, these sort of apps, I mean, the abelianization is finitely generated. So you have sort of finite dimensional space of maps. Now, the idea really here was to examine quasimorphisms, which are inherently infinite dimensional and can actually capture more of the structure of the group. And so we're sort of really like using asymmetry here, and we're using non-commutativity to really construct these statistics.
So do you have a theorem about quasimorphisms on G, on gamma?
Yes. So I have a theorem about quasimorphisms on G, and I'll say that I'll just erase this and say here. And so you can say the same thing about any quasimorphism. So in the same setting, if and only if for every quasimorphism, this from G to Z, this limit of this expectation it's really the same statement. Of n times the drift is equal to the same thing for the second measure. And the same thing for the variance here as well. So this is excitation with respect to the second measure divided by the drift of the second measure. Yep.
What is a quasimorphism?
Oh, I'm sorry. So a map from a group to Z is a quasimorphism if it's within bounded distance of a homomorphism. If there exists some d greater than 0, such that for all gh in the group, p of gh minus p of g minus p of h is bounded by d.
This means that it's close to a homomorphism?
Yeah,
It's not necessarily a homomorphism, which is close to.
yeah, exactly.
That's
Yeah, yes. And that's sort of the important thing. So the trace of quasimorphisms on hyperbolic group will be infinite dimensional, for instance. And I guess one example you can have is, say you take a free group and given some word, you just count the number of A's minus number of A inverses. And you can make sort of, this natural homomorphism. But in a hyperbolic group, you can make variants of this work, where you count sort of long segments minus inverses. So for example, if I take this like this finite CGD minus CG inverse D, then I will get a quasimorphism. And this is actually the construction that Pespina and Fujiwara have. Right. And so I have a couple minutes left.
No.
Oh, I'm sorry. Okay. Okay.
You want to say something more? You can.
I will just very, very briefly say a word about the proof. And that the proof actually uses very simple inputs from hyperbolic geometry. So you take two measures which are singular at infinity, and then I'll construct quasimorphism using the probabilistic method. But the only input I have is that the hitting measure are both non-atomic. In particular, using this, plus the fact that the action on the group is sort of expanding, it tells me that if I have a point which is sort of very close to the boundary, I ask what is the probability that my limiting point here is not within some sort of shadow, and this is absolutely minuscule, just by a non-atomicity. And so what I do is, once I have singularity, I will take some open set A, which nearly witnesses this, in the sense that nu1 of A divided by nu2 of A is extremely large. And then what I do is I examine the function f which is the f of g, which is one is the probability that if you take the first random walk that g limits into A, or the second random walk, f1 and f2. And the point is these functions are both martingales, which converge either to 0 or 1 at infinity. And so what I do is I take this measure and I stop it once it passes some very, very large size. And so these martingales have almost stabilized. And then I cover this with many balls. And then using essentially the fact that one of these things is much larger on some other thing, I can, by the pigeonhole principle, I can construct such a quasimorphism. And you have to, you need to pass from some finite scale to actually propagating the sort of discrepancy which you can do using some hyperbolic geometry. But that's just all I'll say about the proof, and I'd be happy to discuss it with anyone afterwards. But that's what I want to say.
You have something to say about that conjecture?
One is that, so this came up by this method I was trying to show to prove this conjecture, and essentially the idea was that like, I wanted to take like two hyperbolic elements that cross each other, and I wanted to construct such a G using essentially something which is, and this part is very vague. I want to take two elements A and B, which are hyperbolic with crossing axes, and I wanted to examine essentially the elements, it's called A and B, A, B to the 100, and the elements A to the 100, B to the 100. And I want to say something essentially along the lines of the green distance between these and the identities to be roughly similar, but because, I mean, because the hyperbolic metric is not perfectly additive like the word metric is, every time I pass from one to the other, the distance I travel gets smaller by some definite amount, and so I can use these to construct.
I'm a bit confused about the conjecture. Is it about a finitely supported or finitely supported inside a lattice?
Inside a lattice.
Okay. So Bergen disproved it without that.
But without the lattice. Yeah, so you need the lattice.
Is there any reason to believe this conjecture in general?
I mean, there are vague.
Absolutely any reason to expect that for any lattice in a league in a group, for any finitely supported measure, the corresponding stationary measure would not be absolutely continuous. Any shred of evidence?
Well, other than
I kind of agree with you. It's like a strange condition.
no, I agree. It is a strange condition. I mean, it was sort of unclear to me whether or not it should be true or false. I mean, I was wondering for a while, maybe it's just false because we're really bad at the inverse problem, for instance. But I think one reason you might expect it to be true is just because sort of the failure at being able to actually like do the inverse problem. I mean, maybe like first inverse construction was this discretization of Brownian motion, and what you might expect is that if you have like a lattice, once you try to discretize at some finite scale, there will be some sort of discrepancy. And as you run the random walk, this will sort of propagate larger and larger. And all the statements of the form actually disproving this have been along these lines where you have some discrepancy and you manage to find it. But I agree, like it's still not, I wouldn't
It
bet.
might be true for SL2, but I would stop.
Sorry, SL2. No, I have no idea whether it's true in general, but SL2 maybe.
I understand Vadim has some question or comments for the talk. Maybe he can, I understand his micro is unmuted. Maybe he can ask
Yeah,
online.
can you hear me? Hello?
Oops, sorry, the TV turned off.
This is gonna be good. This is great.
Okay, my microphone is on. Can you
That's
hear me?
working. Working.
So first of all, a little comment about that conjecture of mine about singularity. So the background is that actually it comes from Riemannian geometry, because if one has a compact negatively curved manifold, then there are actually not even three natural classes of boundary measures, which are the visibility measure, the Patterson measure, and the harmonic measure. And there it is known, at least for surfaces, that equivalence of any two measures from these three only happens when the curvature is constant. So that's more or less what the origin of this conjecture is. And my question is the following. So you were talking in terms of harmonic measures. However, if one forgets harmonicity of these measures, does your technique give anything for the question of identifying when different boundary measures are singular? So that let's say if we are talking about finitely supported random walks in the cocompact case, then that's the class of Gibbs measures, essentially, that we are talking about, right? And so let's for simplicity talk just about hyperbolic groups, okay? Then there is the class of measures on the boundary which arise as Patterson-Sullivan measures of various metrics roughly isometric to a given one. Are the harmonic measures you are talking about the ones arising from the first moment random walks? Are they, I don't think they are necessarily from this class, right?
So I believe, I'm not entirely sure, and I think there's upcoming work of, I think, Stephen Cantrell, Alex Eskin, Wendy Penn, and Kaz Rafi that construct for Patterson-Sullivan measures on the boundary of a hyperbolic group, measures of finite first moment, such that these are the harmonic measures. But I think it's still sort of ongoing, and I don't know. I mean, I think if you forget the interpretation in terms of harmonic measures, I mean, the point here is you need some sort of renewal structure in order to say that once these things are different on some scale, then you can propagate this in the right way. And so I believe that given Patterson-Sullivan measures on the boundary, using the appropriate thermodynamic formalism, one might make such a thing work, but I would have to think about it.
Yeah, well, the reason I'm asking is that there is a very nice description due to Alex Fuhrman, which describes quite explicitly when two Patterson-Sullivan measures are equivalent. That's if and only if the corresponding metrics are, what's the right term, equivalent.
Right. Right. I see. Okay,
So,
then, sorry. Yeah.
No. That was the motivation of my question.
Okay, then I think that you can say something about like constructing. I mean, looking at these maps arising from quasimorphisms and using that to witness the fact that these two Patterson-Sullivan measures might be in different classes. That's the question. I believe so. I would have to check, but I wouldn't be surprised if that's true.
Okay, but do you know whether the harmonic measures arising from, let's say, symmetric random walks with a finite first moment are in that class of the Patterson measures arising from roughly isometric metrics?
Oh, okay. What do you think? I'm not certain.
Okay, thank you.
Thank you.
All right, let's thank Kunal again.
There is also a question of Timothy Benar. And he asked, can you repeat the connection between CGD and quasimorphism? That is connection between the two theorems.
Oh, sorry. Yes. So the point is that you can construct quasimorphisms by taking CGD minus CG inverse D. So this is in the original paper of Fujiwara. So I believe it's called the second bounded cohomology of a group acting properly on a hyperbolic space. So this is the relation between these maps and quasimorphisms.
I think, yeah, we're ready for break. We're